السلام عليكم. رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني ويفقهوا قولي. رب زدني علما. This again presentation is the continuation of chapter 5. In last four lectures, we have been covering chapter 5 step by step. And we talked about centroids, centroid of the system, centroid of masses, volumes, areas. We talked about how to find centroid of a composite system. And then we started focusing on the elements, some special topics regarding the beams. And in the previous lecture we talked about beams, a definition of a beam, and then we talked about external forces of the beam. Now during our lectures, somewhere in chapter 4 you came across structural loading, and in there we talked about internal loading of a beam. And in those internal loadings, we talked about two specific type of internal loadings. Number one, if you remember it carefully, was the tension when the beam is going through extreme pull on the axial faces, and compression when two forces are trying to push the two faces of the beam, axial faces of the beam, inwards, trying to compress the entire structure. Now these two internal effects or internal loadings are very common, but some other loadings, some other internal forces are still yet to be discussed, and in this topic we are going to discuss some of those internal loadings which are a vital part of our structural design. Now in these internal loadings we are going to talk about three different types of internal effects. Number one is a shear effect. If you remember carefully, two forces acting in opposite direction causing a shear phenomenon. The shear effect is for the structure, it is there, but they have to act in pairs. Now all these loadings are acting in pairs. You've got shear forces, you've got bending moment, you've got torsions. So in this book we are going to talk about shear first. The shear is defined by the variable V, capital V. It acts in a, you can say, transverse section of the beam. If you remember, tension and compression act on an axial sections, while shear forces acts on the transverse. Now you have to remember, if you take this beam, imagine they're straight, this force of the beam are the axial faces, so they are not working on axial side. Axial forces, on the axial faces you have tension or compression. Now on the transverse sides, if you look at the above surface and lower surface, and two forces equal and opposite magnitude acting in a direct only opposite to each other at the same point, you will generate a phenomena called a shear phenomenon. Then we have a couple or a bending. Now you have to remember, even in the beams, moment is going to act as a couple, and it is defined here as M. And you can see they are equal and opposite in magnitude. Similarly, we have a third effect called torsion. Torsion is acting on the axial faces, but the effect is prominently on the transverse faces. If you can see, they're trying to tend away. It's just like you take your plastic ruler and you take to either ends and start rotating it, and you'll see the bend. This bend is called a torsion. Now, if in reality, if you look at the combined effect on any surface, you will see the figure here, and you're going to see the combined effect of these loadings. And here you can see the effect of a moment couple, a torsion, and the shear force acting on a beam are the internal effects that is being generated. Now you have to understand, if you are compartmentalizing any of these forces, or you're trying to work through the calculations of any of these forces, they always act in pairs. This means if you have assumed the direction of one force, that's a shear force, is acting downward, then the conjugate, its counterpart acting on the other side, has to be equal and opposite. then it does not matter whether it is supposed to act downward or it's supposed to act upward. No, the first assumption from where you're going to start your calculations will be carried on till the end. The only way these directions will be reassigned is through algebraic calculation. So don't need to worry about what is going to happen, whether my assumption is right or wrong. The signs are going to fix themselves automatically. Now let us look at what is happening at the part when we look at the point where shear force is acting or force is acting. And when we take a beam and say the beam, bisect the beam, we are going to say there is a couple phenomena. This is the couple, equal and opposite, and equal and opposite shear forces. This is how the actual uh, uh, bisection of the beam would look like. Now when we talk about moments, the beam, and so you can see the figure on the right, you can see the beam is going through a couple throughout the cross section when this type of action forces are acting on the beam. Now here he has taken an H beam or an I beam, and the upper surface is going through a compression while lower surface is going through extension or expansion. You can see the couples are working equal and opposite direction. If you look at this thing, it's going to be acting this way, and this is going to be acting this way. In reality, your beam is static, it's in equilibrium. If this structure is no longer in equilibrium, it is going to fail, and the way it is going to fail is through a shear phenomena acting somewhere where it is going to have a maximum force on either side. Now before once we have calculated or understood the idea of what are the shear forces, the moments and the torsions, then we need to understand how to develop the diagrams. Diagrams are a vital part of these calculations. Shear force diagrams are very important. Now the length of the beam provides information necessary for the design analysis of the beam. Now it is particularly when we are talking about the bending moments. The maximum magnitude of bending moment is usually an important consideration during the design of the beam. Now this is important because we have to identify where this moment or couple or shear force is acting, number one. Number two, what is the magnitude? The variations in shear and moment are best shown graphically. That's why we need the bending diagrams. Now the expressions for the shear and moment, when plotted against the distance of the beam throughout the transverse section, we are going to get a shear force and a bending moment diagram for the beam. Now these are the following steps which we are going to discuss. Number one, we have to determine the shear force relations, which is the first step is to develop a shear force and momentum relations on the beam. The values of all external reactions on the beam by applying equations of equilibrium to a free body diagram of the beam as a whole. You have to understand this thing. Whenever you are talking about a beam, you need to draw a free body diagram. A free body diagram will establish a certain external forces acting on your beam. With the help of those forces acting, you can develop a behavioral free body. From that you can develop a equation of equilibrium, which is going to generate a shear and moment acting on that particular section. Next, you isolate that portion of the beam either on the right or on the left, and then you move across the transverse section of the free body diagram. Now these equations for each section is going to develop an equilibrium equation. Remember, there are only two types of equilibrium equations. Sum of all forces should be equal to 0 and sum of all moments should be equal to 0. Finally, once you have developed, I will repeat it again, once you have developed a free body diagram, established all reaction forces, external forces applied or in response to the joints such as pin joints, roller joints or concrete sections, they all will generate a reaction forces. Once you have established a free body diagram, you're going to start isolating it. Then you're going to start isolating your each point. You're going to either start from the right hand side of the beam or the left hand side of the beam. From there you're going to move from section by section. You have to understand one more important point. Once you have developed a free body diagram, established all the forces on the beam, develop all the equations, that is equilibrium equations of the beam, then you have to understand, once you open for a shear force, that shear force act in pairs. This means the conventions you have choose from one side, equal and opposite is going to go through the next side. You will not change in order to suit your uh, equation balancing. Once you have assumed this is the direction that shear force is working, you have to keep that direction continuous throughout your calculations. As I have said before, changing the assumptions within the problem is going to create problems, and it is not a good solution. Now, these are the general loading shear relations which we are going to talk about. General loading shear and moment relations. Now, we know the general form of loading W can be in any shape. So here in this figure, we have a very generalized form of load distribution over an element. And what we have done is assumed a very small fragment or segment, that is dx, with the thickness dx. Now, in order to do that, what we have is the shear force acting on either side of this component and a moment. Both moment, that is the couple acting on the either side of the faces. We have to remember, once the convention is followed, we have to follow through the entire way of our calculations. So we know, since the system is in equilibrium, the shear force acting upward and the shear force acting downward should be equal and opposite in nature. So we are going to start from the far left side, from this side, left side. So we have the definition for shear force, that has sum of all forces along the y-axis should be equal to 0. So we have V minus W V dx. W is load per unit length, and for the length dx we will get weight acting downwards, minus, and minus dvx. As we know, this whole is acting downwards. This entire system becomes an equilibrium equation. And if we generalize this form, say V is going to cancel out with V, what we are left with is the W, that is load distribution, is in fact minus dV by dx. This is a very generalized form and load spread. So we can actually develop and derive the equation of a very uniform load distribution, such as a triangle or a square, and we can solve for the shear forces based on the uniform load distribution over the length of the beam x. And if we open this thing, and you can see, if you move to this part, we will say in an integral form, there is V naught by V dV minus x naught to x dx. Here W is a function, W can be a function of x or could be a constant. Once we have calculated the shear forces, now we are going to move towards how to calculate moment. Again, starting from the far left side, we will have the moment, that is M, acting clockwise. So we will have M, and assuming this is to be the positive side, so we are talk about the force, that is W dx, this force acting at the center, that is the concentrated force of W dx acting at the center. This, and the distance from the far left hand is x by dx by 2. This will create again a counter clockwise movement, right? And this means a clockwise movement. Then we are left with this force, that is V dV. This is also acting downwards, and it's also going to create a clockwise moment. The only moment that is acting at the other side is minus M dm, and that is this component, and hence we will complete our moment equation. So, in order to solve this equation, if we start solving it, you will find out we can easily drive these equations, and we'll find, and it will turn out to be something right here, that is V is equal to dm by dx. Now from here you can easily solve for the equation, and you can further open it, and you'll find out the equation on the far right is the final form of the moment equation with respect when v is a function of x. Now when we are solving these things, you must remember, when we have w, that is weight or load distribution per unit length, it is just a function of x. So w is a function of x, and this has first order equation. V will become, v is a function of w times w x times x. V will have an order of x square. Similarly, when we talk about moment will have a higher or third degree order of x cube. And if we solve this thing, you will find out that w, or you can say moment, is in fact can be constant k times x cube, whereas a w will be defined as k times x. Now with this information in mind, we are going to solve a few examples. Now I have just introduced directly shown you here the example of the book. This is the 9th edition of Medium Trade, and you can see in chapter 5 this example is to show and to understand how the author is solving the problems. Now let us solve this problem. Determine the shear and moment distribution produced in a simple beam by 4 kN concentrated load. So we have a concentrated load acting at a distance of 6 meters from the pin joint. So first thing is, we are going to develop a relation how the reactions at this position A, let's say this is 1 and let's say this is 2, how they are working. First thing is, we are going to draw our direction vectors. Sorry if my representation is not very accurate, but I hope you get the idea. So this is the y-axis, this is x-axis, and this point is origin, the pin joint. From here you can say, assuming sum of moment about point 1 is equal to 0, so you have 4 kN acting downward. This is going to create a moment clockwise, and 2 Newton is going to create a moment counterclockwise. They should be equal and opposite. As the system is in equilibrium, you can find the value of R2. Now assuming that at position 2 sum of moment is equal to 0, and you're going to apply the same technique, that 4 kN by multiplied by 4 meters can cause the beam to rotate other way around, and this reaction force at point 1 can with the reaction force R1 can cause the beam to move in a clockwise direction. And with these two equations you will get the two reaction force magnitudes. Now we have all the external forces known. Based on this information, we can further find out the shear forces. The first thing is to fragment your beam. Very simple. If once we have developed the free body diagram and identified the external forces, what we have is the first segment right here on the left side. And we know, if we for the reaction R1, for any distance away, let's say that distance be x, we have a equal and opposite force, shear force, and a corresponding moment acting on the beam. So we can define that V is equal and opposite. So V at this point will be 1.6 meters equal and opposite, but the moment has to be also equal and opposite. So 1.6 kilonewtons times x is equal to m. This will provide us the information of the shear force and the moment. Now let's go to the other side. On the other side, after when we traveled across the beam and we reach the other reaction point 2, that is reaction position 2, we know that V is going to act upward and has to be in this direction of V is upward, because we have chosen this direction to be positive. So when we cut the beam into parts, these should be in equal and opposite direction. This is directly related. So if this direction of the first stage would have changed, then you would have the opposite direction of this value. But as we have assumed this value to be true, then this type of force is there and will hold for the direction. It is considered, you can say, true for the direction. Now again, so we know this direction is determined and this also determined, so V has to be minus 2.4 kilonewtons. It is automatically fixing its direction. Now we are going to talk about the moment generated by the moment generated at this side. We know that is 2.4 times 10. 10 is the total length of the beam minus x. At any distance x will generate a counter moment. It has to be equal and opposite to this moment, and we have derived the secondary equation of moment. Now from this value we can find the value of x. But this x is a very generic form. So let us start from moving and adding the value of x, 1 meter, 2 meter, 3 meter, 4 meter, 5, 6, and from there you can actually calculate and develop a figure of shear moment. So using the equations, let us develop the first set of equation, and as you can see, from here to the specific point 6, that is where the 4 kilonewton meter was acting on it, our shear diagram indicates it is a constant of a constant magnitude, as v is not a function of x, and it is again going to minus 2.4. This discontinuous jump creates a large jump in moment. As you can see, the moment is a function of x. It's a straight line. So up to a certain point, that is 6 meters, it will have a straight incline moment. And after, if you look at this equation, the second part at R2, this is a sloping moment. And you can see this from 0 to 6, the line is going up as the moment is increasing, and from 6 to 10, the moment is going down. These two diagrams are derived from these equations. Now, let us look at a little more complication when W is given as terms of function of x. Now here, the cantilever beam is subjected to the load intensity, that is force per unit length, which varies. W is defined as W naught, that is a constant, that is initial load distribution, W naught, sine pi x by L. Determine the shear force B and moment M as a function of x by L. Now, you have a function of W, that is load distribution, and it is provided right in the question. And this function is a function of x. So we can easily find the value of V naught, and we know for value of V naught, where V naught is where the W is a function of x, we can move this x from 0 to maximum length L, and so we are going to integrate W from 0 to L with the dx as a function of x to dx. So we will find the initial value of V naught, and here you can see sum of forces x is equal to 0, sum of forces along y-axis is equal to 0, V naught minus dx. So we have no V naught here is going to react upward, and corresponding reaction, since it's a single cantilever beam as shown in the figure right here. And for this V naught, we have found the value of W to x by under root 0 to L. Since it is just supported by one end of the beam, so this situation, this equation holds true. And we solve this integral sign, and we find out a constant value of 2 omega naught L by pi. And then we are going to find the value of M naught, the initial value, and again we will have the function of x times W dx, right? And when we open this thing, we will get W naught x sine pi x by L dx. And if you integrate it, you are going to get the value of, just open it according to the integration which you have learned in your basic mathematics, and you will find out this is the value of minus W naught L squared by pi. So we have the initial values of M naught and V naught. And then now we are going to find a generic form of a generalized equation for this particular load distribution. And here we have it, as you can see. Yeah. M naught is written as M naught, well, as you can see, equation right here, where's my pointer? Yeah, this part of equation, you can know v naught to v. We have the value of v naught. We are going to write v as a function of x here, and we have the value of w naught as a function of x. And we open this equation and we find out that the derived equation, or you can say after solving and through going through the algebraic calculations, we'll find the value of v as a function of x. Further, we are going to solve for using the same moment equation, that is dm v dx, and we are going to solve for the moment equation. And these are the two generalized equations. When we take these two generalized equations and draw a diagram, we can see that based on x cos, when x is equal to 0, cos would have maximum value of 1, and you can get the value, that is v naught by omega naught L. And as it moves away from 1, away from 0 to higher radians, and it reaches the other cos is equal to 1, you can see it is reducing. The shear forces are reducing, but correspondingly your moment forces are also increasing. At 0 you have negative moment, and as it goes away from the joint of the cantilever, the moment is increasing gradually. This is also now we are going to talk about another example where you have to find or drive an equation. We have multi or both type of equations for load distribution. In this particular example, you have to draw the shear force and bending moment diagrams for a loaded beam and determine the maximum moment M and its location X from the left end. Now we start with basic thing, a free body diagram. And if you see the free body diagram, when we are solving for the free body diagram, we have to solve for the external forces. Now if you look at this figure, starting from the left hand side, that is from the pin joint here, you have a triangle load distribution, then you have a square load distribution, and then you have a roller joint with a reaction force upward. So from this pin joint you can see you have a force along y-axis, you have a force along x-axis, and you are going to develop a set of external forces. So for the triangle, you know the overall area just by the triangle is the 4 feet, that is the base, times 100 pound per feet divided by 2, so you get 200 pound force acting downward. Now where is the center of this triangle? As you all know, 1/3 of distance from its base. And if you look at this, thing, this side is the base and it has 1/3. So what you will have is the total length to this point here, 8. So how much is this thing? You know, divide 4 by 3, so to multiply by 2, and you will get 8 by 3, 2/3 of the distance from the upper end. Then you have a simple uniform load distribution of 100 feet at a distance for 4 feet, and what you will have is 100 times 4, and you got 400 pound force acting at the center, that is half of the square. And then all the external forces have been introduced in this figure. Now remember, as previously, R1 and R2 can be simply calculated using the equation of moments, and sum of moments at R1 is equal to 0, and then sum of moments at R2 equal to 0, and you will got the corresponding values of R2 and R1 respectively. But now we have to develop a formulae for the far left hand element for shear force and moment forces. Now for shear force, you know, at this point, pin joint 1, we have 247 pound force as a reaction R1, and just immediately to the right at a distance x, let's say, you have a set of shear forces, that is V, and moment acting on it. So what is the load distribution of this load distribution on this particular segment? We know the load distribution is defined as, if you remember correctly, 4 times, that is x times height divided by the base into height divided by into half into base into height. This is the load distribution over this region. And you know, if you remember carefully, let me write it right here. Now, in order to get this equation, V is equal to 427, you have to understand how did we or this author came to this conclusion. The first thing is, let me use an eraser. Let's finish this thing. How did he got this thing? If you remember, this is a line from 0 to height 100. So we are going to find the slope of this line, and you know y is equal to mx. And if you know the value of m, you can find out m to be 100 divided by 4. Now this is the slope of the line. And if you make the function of this w, and you will find it to be 100 divided by 4x to be the function that is defined by this line. Now, if you remember correctly, if you remember in my previous slide, I said w is equal to minus dv by dx. As we know, w is a function of x, which is equal to right here, w is equal to 100 by 4x, and you integrate it from 0 to x. You are going to get an equation based on these values. 0, as you know, w is, you will find the value of 0 to x. It will turn out to be 100 by 8x squared, which is equal to, in fact, will be equal to this figure right here. The other side, dv, as you know, that if you take integral from v0 to v dv, so we have the value of v0. v0 of the value is r1 in opposite direction. So what you will get is this final form of equation right here. So we have found the value of shear force. Now we are going to develop an equation of moment. An equation of moment is the same way as shear force. We know the moment is sum of forces acting clockwise, and we are going to start clockwise and counterclockwise about the left end of this point. So sum of moment about r1 are to be considered from here. If you saw 237 is passing through the point, so no moment, but this 12.5 meter force, this force is acting downwards, and it is going to rotate on the other side. And this is 12.5 from the triangle x square, that is the shear force acting at a distance of 2x by 3. You don't need to find 2x by 3, but we can get how you get this equation, you're going to find out. So we have this equation, and then we have the shear force, that is V acting on it. So if we integrate the same way, if you remember correctly, that V is equal to dm by dx. So here v is a function of x. You take this v and you integrate it with respect to x. We are going to find this value, and this value is equal to 12x squared by 3 x and 247x time, and then you will get m is equal to m, that is m naught by m. And you have the value of m naught. No, you don't have the value of m naught, because m naught is going to be calculated through these values, through this particular relation, and we have found the value of our m. Now this for this particular reason, we need to know that this particular relation holds for 0 to less than x is less than 4 feet. After 4 feet, the shape of the distributed load changes, and now we have to solve this thing for. Now we are going to solve this behavior of, or the distribution of shear forces and moment forces from 4 feet to 8 feet. And for this particular set of equations, you remember the load distribution is x minus 4, that is from any length from 0 to 4. Minus 4 means the triangle region has been eliminated from 4 to 8. In fact, And if you solve the same way as I've told how to, as discussed previously, you are going to get the equation again for load distribution x integrated with respect to d of x, and you are going to get these values 447 minus 100x. And you take this equation and you further integrate with respect to x, you are going to get the value of moment. And if you can see, the moment is a function of x squared. So we have now done the segment from 0 to 4 feet, from 4 to 8 feet, and now we're going to solve for the external forces. And again we solve for the external forces at the roller joint, and you're going to find out this is in fact going to be the shear force of minus 35 pound force and a moment of a single order linear moment. And then we are going to solve for the fourth part, and for the fourth part you're going to find out that the force the value of 300 meter has been 300 pound force has been given. The only thing is the moment which is missing, which we have calculated to be the maximum at that point. Now maximum is at that point 4. We have calculated for the moment. Now we are going to use our equations and we are going to distribute our forces. We're going to write the equation of the general moment diagram, moment forces, and the shear forces, shears and moment forces, and we are going to develop a curve from 0 to 4. If you remember, the first set of equations is going to work from 0 to 4 up to the point here. From 4 to 8, the second set of equations is going to work, and as you remember, from 8 to onward there is a constant force that is of minus 353 pound force, shear force acting on it. And once at the roller point we cross it, the roller point, we will have a constant 300 pound force acting at the edge. So this is our shear diagram. So using the second equation, that is the equation right here, from 0 to 4, from 4 to 8, and then from 4 to 8 we have the equation from again 4 to 10. Sorry. 4 to 10, if you remember it correctly, right? And from here we have the moment curve from the first 4 feet, and from 4 feet to the next part. It's amazing that they are of second order. If you look at this thing, x cube and then x square and up to 8 feet, and then it's goes straight line, as you can see from this equation. And from after the roller point, it just goes back to the 0 point. So this is how you have developed a generalized moment and shear diagrams and moment diagrams. This is a bit tricky concept to comprehend, but if you have any questions, feel free to contact me, and I'm going to share certain numericals with you in future. Thank you very much. Assalamu alaikum.